Assalamualaikum warahmatullahi wabarakatuh, and very good day to all of you. For chapter number 4, part number 2, we will start to discuss about thermodynamic of the axial turbine. For this slide, I will explain about the thermodynamic of the axial turbine stage, especially about the relationship in terms of enthalpy value for the nozzle and also for the rotor in a turbine stage. So the figure shows a turbine stage that consists of what we call nozzle or stator and also the rotor. So the rotor will involve I call the rotational speed that shown by the u vector. And also you can see the number represent, for example, number 1 represent the condition at the inlet of the nozzle. Condition number 2 represent the condition at the outlet of the nozzle and also at the inlet of the rotor. And condition number 3 shows the condition at the outlet of the rotor. And also we can see the direction of flow, gas flow in and also gas flow out in the diagram. Okay, so now I will explain about the work done on the blade by the gas that flow through the turbine stage. So for the stator or nozzle, in terms of work done by the fluid or by the gas, there is no work done on the nozzle by the gas because the nozzle doesn't involve any rotational movement in the turbine. Okay, so we will have no work done in the nozzle row. So in terms of formula, so delta Wn work done for the nozzle will be equal to the stagnation enthalpy difference H01 minus H02 will be equal to 0. Okay, for the nozzle. So now in terms of enthalpy relationship for turbines, nozzle or stator, so we will have stagnation enthalpy at condition number 1 will be equal to stagnation enthalpy at condition number 2 for the nozzle or for the rotor, for the stator. So this is the relationship in terms of enthalpy for the nozzle or for the stator. So in terms of statement, full statement for this enthalpy relationship, so the stagnation enthalpy remains unchanged through the stator or nozzle of an axial flow turbine. However, for the rotor row, because the rotor row involves rotational movement, rotational speed, work done on the rotor by the gas will be not equal to 0. Okay, so we will have work done on the rotor by the gas in the rotor rows. Okay, so in terms of formula, so the work done on the rotor will be equal to delta Wr equal to stagnation enthalpy difference H02 at condition number 2 minus H03 at condition number 3, and the value will be not equal to 0. Okay, so now if you consider a turbine stage, where a turbine stage consists of one nozzle row and one rotor row. So now the condition in terms of inlet and outlet condition for a turbine stage, we will consider condition number 1 as the inlet of the turbine stage and condition number 3 as the outlet condition for the turbine stage. So in terms of work done on the rotor for a stage, so we will have this formula where work done formula delta Ws for the turbine stage equal to stagnation enthalpy difference H01 at the inlet of the stage minus H02 at the outlet of the stage. Okay, so because in the nozzle there is no work done, and the relationship in terms of enthalpy that we obtain for nozzle is H01 equal to H02, substitute this equation into the equation for delta Ws above. So we'll get delta Ws, I call the work done on the rotor for a stage, is equal to what I call enthalpy, stagnation enthalpy difference at condition number 2, H02, minus stagnation enthalpy at the condition number 3, H03. So if you refer to the Euler equation that we have learned in previous chapter, so the work done on the rotor for a stage also equal to U multiplied by Cy2, Y component for C2 vector, plus Cy3, which is referred to Y component for C3 vector. So the component for the vector are shown in the figure, in the velocity diagram figure. So the diagram shows the velocity diagram at the inlet of the rotor and also at the outlet of the rotor, as we learned in previous slide. Okay, so from the figure we can see the component for blade speed U, the component for Y component for vector C2, and Y component for vector C3. Okay, so from the equation that I mentioned for the work done on the rotor for a stage, so if you combine the equation, so we get this equation where H02 minus H03 equal to U Cy2 plus Cy3, where this equation actually the equation for work done for a stage. However, if we look at the number of the enthalpy that involved, such as H02 minus H03, so H02, so 02 or 02 actually is the inlet condition of the rotor, and 03 is the condition at the outlet of the rotor. So this equation also similar as the equation for work done on the rotor. So both a stage and also the rotor will use the same equation due to no work produced or no work done on the nozzle by the gas. Okay, so now our aim at this moment, we want to derive a special enthalpy relationship for the rotor. Okay, from this equation, so if we implement the velocity diagram and also the stagnation enthalpy equation and the relative stagnation enthalpy equation, so we will get the relationship in terms of enthalpy based on relative velocity, where we have H2 plus half W2 square equal to H3 plus half W3 square. Okay, if we refer to the relative stagnation enthalpy formula, we can replace the terms in the equation with the symbol of relative stagnation enthalpy. Okay, we can see that we have a new relation in terms of enthalpy, where relative stagnation enthalpy at 02, condition number 2, equal to stagnation enthalpy, relative stagnation enthalpy at condition number 3. So if you look at the number, so the number of the condition actually involved with the condition at the rotor. Thus, we will have special enthalpy relationship for turbine rotor, where the stagnation enthalpy at the inlet of the rotor, relative stagnation enthalpy at the inlet of the rotor, H02 relative, equal to relative stagnation enthalpy at the outlet of the rotor, H03 relative. Okay, in terms of statement for the rotor, so we have the relative stagnation enthalpy remain unchanged through the rotor of an axial flow turbine. So the equation, the enthalpy relationship that we obtain here for the nozzle and also for the rotor can be used to simplify the calculation involved with axial flow turbine. Okay, now we will discuss about stage losses and also the efficiency for the axial flow turbine. Stage losses and efficiency for the axial flow turbine. Okay, so before this we already know that for the turbine there are numbers of equation for the efficiency. Okay, however for axial flow turbine we will discuss two type of efficiency. First, the total to total efficiency mu tt, and also the total to static efficiency mu ts. So before that, in order to understand the equation in terms of the parameter involved, we need to study, or we need to discuss about the HS diagram. So the HS diagram will describe the process involved, the condition involved in the turbine stage during the expansion process. So the figure shows the arrangement of the nozzle rows and also rotor rows for the turbine stage. So we have the condition of flow at the inlet and also the condition of flow at the outlet of the turbine stage. For condition number 1, in terms of pressure, we have two types of pressure. So we have stagnation pressure P01 and also static pressure P1. For condition number 2, we have three types of pressure. First, we have stagnation pressure P02, relative stagnation pressure P02 relative, and also static pressure P2. And similarly with condition number 3, we also have three types of pressure: relative stagnation pressure P03 relative, static pressure P03, and also static pressure P3. Okay, so for condition number 3, we have stagnation relative pressure P03 relative, stagnation pressure P03, and also static pressure. Okay, so from previous slide, we already learned that the relationship in terms of enthalpy for the nozzle. So we have H01 equal to H02. So that's why we have point number 1, point 0.01 and also 0.02 in this HS diagram. In terms of value will be the same, and the point will be located on the same horizontal line. So the condition represent the condition in the nozzle where H01 equal to H02, because no work done to the rotor in the nozzle. Okay, similarly to the rotor, so we have the relationship in terms of enthalpy where H02 relative equal to H03 relative. So that's why we have the point for 02 relative, 03 relative on the same located on the same horizontal line. Okay, so in terms of process, expansion process, we have two types of expansion process based on the ideal process. So for the first ideal process, so we have the ideal process that based on total to total value, where the process will involve condition 01 and also condition 03 SS, where SS represents stage isentropic and S stand for the isentropic, and the enthalpy value that involved based on the stagnation enthalpy value H01 and also H03 SS. The second type of ideal expansion process is based on total and static value, where in terms of enthalpy value, the process will involve stagnation enthalpy value H01 and also static value H3SS. In the HS diagram also shows the actual process, where the process will start from the condition 01 to condition 03. Okay, so we already also learned the equation for stagnation enthalpy, where stagnation enthalpy H0 equal to static enthalpy plus half C square. So clearly in the HS diagram also clearly we can see the value of H01 based on the stagnation enthalpy equation equal to H1 plus C1 square divided by 2, and H02 equal to H2 plus C2 square divided by 2. The last one for in terms of stagnation enthalpy, so H03 equal to H3 plus C3 square divided by 2. Okay, another equation that involves enthalpy is the relative stagnation enthalpy, where relative stagnation enthalpy H0 relative equal to static enthalpy plus half W square. Also, we can see clearly in the HS diagram where the H02 relative will be equal to H2 plus W2 square divided by 2, and the value for H03 relative equal to H3 plus W3 square divided by 2. Okay, so HS diagram, in the HS diagram also shows the other type of point that important that we need to consider, such as point 2s, point 03s, and also point 3s. Okay, so the general equation for total efficiency mu Tt is mu Tt equal to H01 minus H03 divided by H01 minus H03SS. That represented by equation number 1, where the equation will involve the stagnation enthalpy value. Okay, so the condition that involved is condition 01, condition 03, and also condition 03SS. So if we consider actual process, so we'll get actual equation. When we consider irreversibility, so we'll have longer and more complex equation that involve loss coefficient value in the rotor and also in the nozzle, the velocity diagram component, the temperature ratio, and also the static enthalpy. So where mu Tt, that represent by equation number 2, equal to 1 plus zeta r, the loss coefficient in the rotor, multiply W3 square plus zeta n, loss coefficient in nozzle, plus multiply C2 square times temperature ratio T3 divided by T2 divided by 2 H1 minus H3, power of -1. So when we consider the actual process, we consider the losses in the stage, including the losses in the rotor and also in the stator. So due to the irreversibility in the rotor row, actual process will involve loss coefficient zeta. So if we consider the enthalpy equation, for the ideal case, the equation will be H for the stagnation enthalpy, H0 stagnation enthalpy minus static enthalpy will be equal to half C square. And for the relative enthalpy, relative stagnation enthalpy H0 relative minus static enthalpy H equal to half W square. So when we include the actual process, so we need to add the loss coefficient component into the equation of enthalpy, where for the actual process, so we will have H0 minus H equal to half C square multiplied by zeta component, and H0 relative minus H equal to half W square multiplied by zeta component. So that's the difference between the ideal and also actual process based on the enthalpy formula. So the involvement of zeta n, the loss coefficient for nozzle, or zeta r, loss coefficient for the rotor, in the equation is depend on the specific condition that involved during the process, where the condition involved is the nozzle, or the condition involved is the rotor. Okay, for the total efficiency, if the temperature drop is very small, so we can neglect the what I call the temperature ratio terms in equation number 2. So we will get more simplified equation as mentioned by equation number 3, where mu Tt equal to 1 plus zeta r multiplied by W3 square plus zeta n multiplied by C2 square divided by 2 multiplied by H1 minus H3 power of -1. Okay, for the total to static efficiency, mu Ts, the general equation will be mu Ts equal to H01 minus H03 divided by H01 minus H3SS. So the equation that represented by equation number 4 involves with two types of enthalpy, stagnation enthalpy and also static enthalpy, as shown in the figures. Okay, so the condition that involved is H01, 03 and also 3SS. If you consider the actual process, So we'll get equation number 5. Mu Ts equal to 1 plus zeta r W3 square plus zeta n C2 square multiplied by temperature ratio plus C1 square divided by 2 H1 minus H3 power of negative 1. If the temperature drop is very small, so we can neglect the term for temperature ratio. So we will get equation number 6. Mu Ts equal to 1 plus zeta r W3 square plus zeta n C2 square plus C1 square divided by 2 H1 minus H3. So these are the equation that we can use to determine total efficiency and also total to static efficiency for the axial flow turbine based on the velocity diagram and also the enthalpy value. Okay, in this slide we will discuss about the Soderberg's correlation 1949, where from the correlation we can obtain the turbine blade losses value. Okay, Soderberg 1949 conduct many tests on steam turbine and on cascade investigation, and extended to fit data obtained from small turbines with very low aspect ratio blading, which is referred to the small height chord ratio. And the correlation can be used to determine the loss coefficient in the nozzle and also in the rotor for the axial flow turbine. So this is the result in terms of graph. The result that obtained by Soderberg shows the correlation between loss coefficient zeta star versus deflection angle epsilon. So in the graph we can see that there are three lines that shows in the graph, where the blue color lines shows the data for T maximum divided by L equal to 0.2. The second one for the data that represented by green dash line for T maximum divided by L equal to 0.15, and the red color dash line is for T maximum divided by L equal to 0.30. So the schematic diagram on the graph shows the blade profile, where we use the graph the figures to show the parameter of T max and also L. Okay, so L stand for the chord length, and T max is actually the thickness of the blade profile. Okay, so the graph specific result for I call the load coefficient value equal to 0.8, aerodynamic load coefficient value equal to 0.8, and the aspect ratio H over B as shown in the figures equal to 3, and the Reynolds number equal to 10,000. Okay, if we refer to the the velocity diagram of a turbine stage as shown in the figure, for this nozzle row, the deflection angle can be determined by using this equation, where the flow deflection angle epsilon n equal to alpha 2 plus alpha 1. So flow deflection angle at the nozzle equal to what I call the outlet absolute flow angle plus inlet absolute flow angle alpha 1. If the condition has the very small deviation angle, the flow deflection angle for the nozzle will be equal to the blade deflection angle of the nozzle, where the deflection angle flow deflection angle for the nozzle more or less equal to alpha 2 prime. Okay, the absolute blade angle, alpha 2 at the outlet, and also the absolute blade angle at the inlet. However, for the rotor, the flow deflection angle for the rotor will be equal to the relative flow angle at the inlet of the rotor plus the relative flow angle at the outlet of the rotor. However, if the condition obtain very small deviation angle, so the flow deflection angle for the rotor will be equal to the blade deflection angle of the rotor. So the flow deflection angle for the rotor will be equal to beta 2 primes, the relative blade angle at the inlet of the rotor plus relative blade angle at the outlet of the rotor. Okay, so for example, if somebody give you the data as shown in the graph, where T over L equals to 0.20, deflection angle for the nozzle equal to 120 degree, and deflection of the rotor angle equal to 130 degree. So you are asked to determine the loss coefficient for the nozzle and also the loss coefficient for the rotor. So from the graph, actually you can determine both the loss coefficient for the nozzle and also loss coefficient for the rotor. Okay, so for example, for the nozzle, we just draw the vertical line at 120 degree, intersect with the blue color line for T maximum divided by L equal to 0.20. So you will get the loss coefficient for the nozzle more or less equal to 0.134. And then for the rotor, where the deflection angle equal to 130 degree, draw the vertical line, intersect with the blue color line, so we'll get the loss coefficient for the rotor around 0.155. Okay. Okay, Soderberg also provide the relationship in terms of formula. So we have two approaches in order to obtain the loss coefficient. First, by using the graph that provided by Soderberg 1949, or we can use the equation, where this equation is the nominal loss coefficient, which is valid for deflection angle less than 120 degree. So we have for the nozzle, nominal loss coefficient for the nozzle equal to 0.04 plus 0.06 multiplied by deflection angle for the nozzle divided by 100 power of 2. And for the rotor, zeta r star, nominal loss coefficient for the rotor equal to 0.04 plus 0.06 multiplied by deflection angle for the rotor divided by 100 power of 2. Okay, so Soderberg correlation 1949 in terms of turbines loss coefficient correction. So in previous slide, we already learned about the correlation that introduced by Soderberg 1949 for aerodynamic load coefficient equal to 0.8 and the H over B ratio equal to 0.3 and Reynolds number equal to 10,000. So we have the formula for nozzle, zeta n star equal to 0.04 plus 0.06 multiplied by epsilon n divided by 100 power of 2, and for the rotor, zeta r star equal to 0.04 plus 0.06 multiplied by epsilon r divided by 100 power of 2. Soderberg also introduced the equation if the value of H over B not equal to 3 but the Reynolds number still 10,000. However, the equation need to involve what we call the loss coefficient correction. So Soderberg suggests that for the nozzle, the loss coefficient that already include the correction for the nozzle, zeta 1 for the nozzle equal to 1 plus zeta n star multiplied by 0.993 plus 0.021 multiplied by B over H minus 1. For the rotor, zeta 1r equal to 1 plus zeta r star multiplied by 0.975 plus 0.075 multiplied by B over H minus 1. So the third equation that introduced by Soderberg is the loss coefficient formula that already include the correction for the a case where h over b not equal to 3, and also the Reynolds number is not equal to 10,000, where the equation can be used for the condition where h over b other than equal to 3, or the Reynolds number other than 10,000, where the nozzle loss coefficient zeta 2 n equal to 10 power of 5 divided by Reynolds number power of 1 over 4 multiplied by zeta 1 n, where Reynolds number equal to rho 2 C2 d multiplied by dH over mu, kinetic viscosity of the fluid, and dH equal to 2 SH cos alpha 2 divided by S cos alpha 2 plus H. And for the rotor, zeta 2R equal to 10 power of 5 divided by Reynolds number power of 1 divided by 4 multiplied by zeta 1R. So all these three equations for the zeta actually provide the value for turbine blade losses, and the value can be used to determine the turbine stage efficiency. So for example, from the formula of total efficiency, and also formula for total to static efficiency, in the formula, in the efficiency formula, we have the term for in term of zeta r and also zeta n. So from the equation that suggested by Soderberg, we can determine the value of zeta r and also zeta n for the equation of efficiency, for the total to total efficiency, and also for the total to static efficiency. Okay, to test your understanding for this part, answer the question below. First question, the general equation for total to total efficiency is based on which parameter? Question number 2, what is the meaning of zeta r symbols? Question number 3, what is the main outcome for the Soderberg's correlation? So you have to answer the question by clicking the link provided in my blog. Remember that you need to know the password in order to open the link. The password was given throughout the video related to this topic. The clue is also given in the link. Assalamualaikum. That's all for part number 2, chapter number 4.